Thank you for the introduction, and I also want to thank Jiao and Fu Liang for the invitation and the opportunity to present our recent works. Which one?
At the bottom one.
The bottom one, okay. Yes. So today I'm going to talk about essentially machine learning force field model for dynamical simulations of condensed matter systems. Many different kind of condensed matter lattice models. So the motivation of our work is these complex mesoscopic textures observed in many functional electron materials, like this MFM image of colossal magnetoresistant magnetites. And this is a near field infrared image of this FeO2 mode insulator and a high TC material, and this skyrmions MFM image of another skyrmion materials. And these nanoscopic mesoscopic textures are not just of interest fundamentally, but they also play an important role in the emergence of these novel functionalities. For example, this mixed phase structure of pre-existing metallic ferromagnetic domains and anti-ferromagnetic insulating domains is important for the emergence of colossal magnetoresistance. Because you already have these ferromagnetic islands, so by applying a small, relatively moderate magnetic field, then you align these ferromagnetic islands, the spin of these magnetic islands, and induce a percolation transition. That's how you can achieve magnetoresistance. And so other examples is like the emergence of high temperature superconductivity and these resistive switching mechanisms. So the goal is to have a microscopic simulation of the space-time dynamics of these nanotextures, which are also try to understand the microscopic functionalities. Right. However, a microscopic simulation of these complex materials, so although our motivation comes from experiments, but we mostly want to just do unbiased microscopic dynamical simulations. So on one hand, to solve these electronic problems, you need to use these time-consuming microscopic many-body techniques ranging from like exact diagonalization, dynamical mean field theory, quantum Monte Carlo, or DMRG. Depends on how difficult, whether there are interactions in your electron Hamiltonian. But on the other hand, you need to do large-scale dynamical simulations like kinetic Monte Carlo, molecular dynamics, or Landau-Lifshitz Gilbert dynamics, and in order to capture these complex patterns at a mesoscopic scale. So usually it's very difficult to do a good job on both ends. So for example, when people use these complicated many-body techniques, usually they assume the systems are homogeneous and they work in K-space, and often they cannot do very large systems. On the other hand, if you want to simulate these pattern formations or phase separation or phase ordering phenomenon, then people usually just use phase field model or time-dependent Ginsburg kind of model, phenometrical models. So it's very difficult to combine both. And recent deep learning neural networks approach sort of can provide a way to bridge this gap and allow us to do large-scale simulation, but with the accuracy of our quantum calculations. So we will show more in the later. So essentially, we will develop neural network models to learn these time-consuming simulations. And the learned model will serve as a surrogate model for predicting the force. Right. So again, the difficulty of this kind of multi-scale modeling is because of the emergence of multiple lengths and time scales in these complex electron systems. So on one hand, we have this first electron degree of freedom, and so we need to use sophisticated many-body problem to solve them. And usually that means that the electron self-energy depends on some sort of slow-varying classical degree of freedom. And here we are talking about two kinds of slow dynamical degree of freedom. One is these are independent classical variables. These are like lattice distortions or local magnetic moments. And we can treat this as classical variables, and they are independent of the itinerant electrons. And another one is this low degree of freedom emergent order parameter fields, like CDW in this case, or emergent superconductivity order parameter, or even like the double occupation in mode transitions. So in this talk, I will mostly focus on the first part. So we have in our system, we have independent classical variables like lattice displacement or lattice distortion or classical spins. So the complexity of our system is actually very similar to this so-called ab initio molecular dynamics in quantum chemistry. So in order to perform this ab initio molecular dynamics, so essentially you integrate Newton equation of motion using like velocity Fourier, but at every time step, you need to solve a self-consistent constant equation. Once you get the solution, then you use this to compute the force. Then the force can be used to integrate to get the next atomic configuration. So you see this part is easy, but you need to do this constant equation solution at every time step, and this is very time consuming. So people in quantum chemistry have been thinking about how you can speed this up for almost 20 years. So the idea is just, okay, this constant equation is very, very time consuming. Then we just develop a neural network to learn how to compute this force. Now with the trained neural network model or whatever machine learning model, then you directly, given the atomic configuration, then you directly predict the force, and this force can be used to advance the atomic configuration. So that's the idea, and for almost more than 20 years, there have been published a lot of high-profile journals exploring different kind of machine learning architecture and neural network architectures. So, so there are two important ingredients for this kind of machine learning force field model. The first one is scalability. The idea is we can only do exact diagonalization or more exact simulation on relatively small lattice systems. And we want to use this to train the machine learning model, and then we want to use the model to do large-scale simulations. So your machine learning model has to be scalable. And fundamentally, scalability comes from the locality principle, or what Walter called the nearsightedness of electronic matter. So as long as your system exhibits this kind of locality principle, then you can try to use machine learning to achieve large-scale simulations. And a lot of linear scaling electronic structure methods rely on this locality principle, for example, kernel polynomial methods or continuum fractions. So they all rely on the fact that the Hamiltonian is sparse, and that's due to, then you can make the methods linear scaling. But machine learning can incorporate this locality principle very naturally into your force prediction. So there are many different ways to achieve scalability. So one we spend a lot of effort is this so-called beta polynomial architecture. This is also pretty much the first paper on machine learning force field approach for ab initio molecular dynamics. And another scalability structure is based on convolution neural network. So you have this convolution kernel, which is finite. And so it doesn't depend on the system size. And once you train the CNN with this finite kernel, then you can use it on arbitrary large systems. And another approach recently attracted a lot of attention is based on message passing neural network, of which graph neural network is one prominent example. So another important ingredient is symmetry. So for example, in molecular dynamics, people use all kinds of analogical model like Lina-Jones model to do very large scale molecular dynamic simulations. And all these classical models, they respect all kinds of symmetries of the system. So if we want to develop a machine learning model, sort of to replace, provides a much better, accurate alternative to this classical force field model, then our model has also to respect all the symmetries. So in molecular systems, the most important symmetry is this Euclidean, three-dimensional Euclidean symmetry. And essentially it's translation, rotation, and also like permutation symmetry of atomic species. But for condensed matter systems, we are talking about lattice models. So the symmetry is kind of reduced to discrete translation symmetry and also on-site point group symmetry. And also we are dealing with like spins and orbital degree of freedom, so they are also internal symmetries. And sometimes these two symmetries are coupled to each other, sometimes they are independent. So in order to generalize this force field model, we need to find a way also to build our own descriptors. Right, so like I said, to achieve, incorporate symmetry into the model, there are two main approaches. One is this symmetry-aware descriptor. So essentially, I will talk more about this later. And another way is just to do equivariant neural networks. Right. So a general architecture for machine learning force field model is like this. So they say we want to study this lattice Hamiltonian. You have electron hopping on the lattice, and you can also have interactions. And these coefficients, they depend on a set of classical variables. We call this phi. And there could be multiple components, and they also sort of need to obey some internal symmetry group. And there's a classical equation of motion for these classical variables. So for example, here we just consider the simplest model A dynamics. So the time derivative of the classical fields is given by the force, which is just proportional to the derivative of the energy. Right. So, so a naive approach to do machine learning force field model is you take the configuration. So here the circle and the arrow are representation of this classical field. And then you flatten them into a bunch of, an array, phi 1, phi 2 to phi n. And these are the inputs you send into the machine learning model. And then we ask the machine to predict the total energy of the system. And then from the total energy, you do derivative, then you get the forces. So that's how you can, one way to implement your machine learning force field model. But this naive approach does not work in the sense that it lacks the scalability. So you need this, you train this model for this particular system size, but now they say you want to simulate a much larger system, then this particular model only works for this small size. So there's no easy way to generalize to larger systems. So a more scalable approach is this so-called Beta-Parineno scheme. And this was first proposed by Beta and Parineno in the context of exponential molecular dynamics. So again, we want to, let's focus on this particular site Ri, and we want to predict the force on this point, lattice point. So based on locality, we assume that the force of this is one important idea introduced by Beta and Parineno. They introduced this concept of local atomic energy. And here we call this the site energy. So this site energy, because of locality, it will only depend on a finite neighborhood around this lattice point. And let's call this Ci. And we fit this neighborhood configuration into the machine learning model. And then the machine learning model will predict this local energy. So now you apply exactly the same trained neural network to every other lattice point. Like you apply this to the first lattice point, you get epsilon 1. To the second point, you get epsilon 2, and so on. And since you apply exactly the same model to every other lattice point, so this approach respects the translation invariance of your system. Now you sum all this local energy, you get the total energy. And this is also kind of like you use exactly the same neural network and build a super neural network. And then you do automatic differentiation on this super neural network, then you get all the forces acting on every lattice point. So this is a very smart way of taking advantage of the locality principle and achieve scalability. Right. So usually in this approach, there are two important components in this machine learning force field model. One is the descriptor, so to take care of the symmetry, and the other is the learning model. You can use Gaussian potential or neural networks. So to train the neural network in this approach, naively, because the prediction is local energy. So naively, we will think, okay, we use the predicted local energy to the MSE of this local energy as the loss function. The problem is that even with exact calculation, one cannot compute this local energy. So in some sense, this local energy introduced by Beta and Parineno is kind of like a latent space variables. But we can compute the total energy and the force. For example, the force here can be computed using Feynman-Hellman theorem. And so the loss function instead is the MSE of the force and also the total energy. So instead of using directly the local energy, we use this as the loss function. And the force is also important because you are going to do dynamical simulation, so it's important to use force as in your loss function. And training is essentially some sort of Model A dynamics of the loss function, but they computer scientist people, they invent all kinds of ways to avoid trapping in the local minimum. Okay, so next I will try to quickly go over the descriptor. So the reason we need the descriptor is because let's see we have this order parameter of classical field configuration C1, and then you rotate it by 90 degrees, and then you fit these two into the machine learning model, it will give you two local energies. But it's not guaranteed that these two local energies are the same, but we know these are basically the same configuration, just rotated by 90 degrees. And so one way to enforce this symmetry in computer science is to do data augmentation. But in that approach, the symmetry can also only be learned statistically. So maybe 99%, but it will never be exact. So the descriptor approach is to generate feature variables which are already invariant under symmetry. That means two configurations will give you exactly the same feature variable, and then you feed the same feature variable into the machine learning model. Of course, you will get the same energy. So that's the descriptor. And in order to achieve this, I had to mention in molecular dynamics, quantum chemistry, people came up with all kinds of descriptors. And for lattice models, we are pretty much doing this on our own. So the most general approach is based on group theoretical methods. So we will use this host time model, which only need to worry about the lattice symmetry, but there's no internal symmetry of the dynamical variables, as an example. So basically, the idea is, okay, this is like these Q variables are like the Brady mode of this oxygen octahedron, and we have this Q variable at every lattice point. And the descriptor essentially is to translate these Q variables within a finite neighborhood into some symmetry invariant feature variables. And so that means that the same feature variables, you will obtain the same feature variable for different, 8 different kinds of symmetry operations on the neighborhood. Okay, so first we decompose all the Q variables in the neighborhood. They form the high dimensional reducible representation of the default group. And then we do irreducible representation decomposition, and we get all these different kinds of symmetry operations. But these are not symmetry invariant feature variable yet. These are just a linear transformation from the Q variable to these F variables. And what kind of invariant can we get? One is, of course, just the amplitude. So if your descriptor based on only the amplitude, this is called the power spectrum. And the problem with power spectrum is it misses the relative phases between different irreducible representations. So the most general set of invariant feature variables is called bispectrum coefficients. And this is kind of like the triple product of three-dimensional vectors. Right. But the number of bispectrum coefficients for most cases are too many, and many of them are redundant. So we came up with this idea of reference IR. So we use large chunks of the neighborhood to compute some sort of averaged distortions. And then we build an irreducible representation based on this average distortion, and then use this combination as the reference. And we can use this to define the phase of different irreducible representation. So now you have the amplitude and the phase, and this will serve as the general descriptors. Right. So what I described so far is, okay, you have your neighborhood into the irreducible representation, decomposition, and then do your descriptor and fit it into a fully connected neural network. So that's one way to do the symmetry. Another approach is just build your symmetry into the neural network and that is the equivariant approach. So the equivariant neural network is such that every nodes in the neural network, they transform according to a well-defined way. And one way to achieve this is just to insist that every node in your neural network belong to a certain irreducible representations. And when you go from one layer to another layer, then you need to maintain this property. And so, so the general transformation from one hidden layer to the next is like this. So here gamma is the type of the irreducible representation. So within the same irreducible representation type, you can have fully connected connections. But you also want to mix different irreducible representations. And so the different transformation property here will be taken care of by Clebsch-Gordan coefficients of the symmetry group. And then these W are the trainable parameters. And once you have this, then you fit it into an activation function. So that's basically how the equivariant neural network works, combined with this better polynano architecture. But implementation is kind of tedious, and also there are no available package to do equivariant. Quantum chemistry people, they came up with this E3 equivariant neural network for general rotation symmetry. But for most of the point group symmetry, you have to do it your own. So my students spent like more than half a year to implement this from scratch in PyTorch. So he came up with two channels to go from one hidden layer to the next. One is a fully connected connection between the same type of irreducible representation. The other is you first, based on the multiplication table of the irreducible representation, you first mix the different IR. And then once you have this mixed intermediate layer, then you do fully connected neural networks. And all the trainable parameters are in this part. So that's how we can implement this. And I think quantum chemistry people, they used a similar approach for the E3 equivariant neural network. Right. So another even more elegant approach is based on message passing neural networks. And like one famous example is the graph neural networks. So the object to be transformed is a graph, and then you can have features associated with each node or edge of the graph. And then you have spatial message passing neural networks or blocks to transform these features. So in our case, so for apply this to the host time model, we only use node features. We don't consider edge features. So the input there would be just the original lattice. And on every lattice point, we have these Q variables indicating the distortions of the local action octahedron. And now you take, for a given lattice site, you take this site and the neighboring 4 sites, and then you fit this into this message blocking network, and then you predict the features in the first hidden layers. Right. And so the connections we introduced 2 independent connections, one to transform the features of the same site, one to couple the features from the neighboring sites, but they have to be exactly the same W. That way you respect the default point group symmetry. And then you use exactly the same message passing block for every lattice point. This also respects the translation symmetry. So then you do this again for the hidden layer, and then at the output layer, you predict either the local energy or the local force, which you can use in your dynamical simulations. So graph neural network is the one which is most elegant and most easiest to implement. For example, the same student, he spent more than half a year to implement the equivariant neural network. He spent like 1 week to implement this GNN. But for dynamical variables with internal symmetries like spin or orbital degree of freedom, then you might need to combine GNN with equivariant for every message passings. Right. So enough of these neural network architectures. So now I will discuss one application. So we will consider this host time model. And here we assume that Q variables, these lattice distortions are classical variables This will be a good approximation, at least for the checkerboard CDW phase of this model. Of course, it will not be sufficient to describe the superconductivity of this model. And so around half filling, the ground state of the host time model has this exhibit this charge modulation, which breaks the G2 sublattice symmetry. And so this is similar to a 2D eSIM model. And even using determinant quantum Monte Carlo, people already verified that the phase transition into this G2 CDW phase belongs to the 2D eSIM universality class. So then the question is, if we want to study the cross-link dynamics of these CDW domains, whether it also belong to this eSIM superuniversality class of cross-link dynamics, right? So just a quick review of what I mean by cross-link dynamics. So for example, if you do Monte Carlo simulation on the textbook two-dimensional eSIM model, so you start from a random configuration, and then you suddenly quench it to like 0 temperature, and you see this formation of ordered domains, and it becomes larger, merge with each other, and this is the cross-link process. And if you compute the correlation function at different times after the quench, and by properly rescale the distance by some characteristic length, then all the different curves they collapse on the same hidden curve here. And this is an example of dynamical scaling. And this characteristic length increases with time according to this square root of time behavior. This is called Allen-Kahn domain growth law. So the same Allen-Kahn domain growth law can also be obtained by doing time-dependent Ginzburg-Landau simulation, assuming this energy functional for the eSIM model. And again, you get this square root of time behaviors. So then the question here is whether the CDW cross-link exhibit the same Allen-Kahn domain growth. So like I said, we build a neural network model. So based on the local lattice distortion, we directly predict the force. And this is the benchmark of our model. So you can see the force prediction is very, very good. And on small systems like 30 by 30, we also did a dynamical benchmark. We run the length-driven dynamic simulation for the lattice distortion based on exact diagonalization and also based on forces predicted from the machine learning model. And you can see that the correlation function at different times agree with each other very well. So now with this model, then we can apply this to very large system, like 200 by 200, and this is the cross-link of the CDW domains. So the different color corresponds to one versus another CDW order states. And then you can see we define this local CDW order to characterize the domains. Right. So if you do exact diagonalization of this size, it will take almost a few months to complete the whole simulation. But with machine learning model, this takes maybe 2 or 3 days. But I have to also mention that there are other linear scaling methods, like kernel polynomial methods can also do the same job, but machine learning is just more general. KPM can only apply to systems without electron-electron interactions. Right. So now the results are of the cross-link. So then we use the correlation function from our large-scale simulation. We compute this characteristic length, and then you can see that they all deviate at different temperatures. They all deviate from this expected square root of time behavior. We still get the power law domain growth, but the exponent are all less than 1/2, and it is sort of temperature dependent. So this is an example that you can get new physics with machine learning enabled large-scale simulations. Right. And the reason why this sort of deviate from the expected square root of time behavior is related to this non-trivial domain wall structures in this model. So for the square root of time Allen-Kahn behavior to be valid, you need to have smooth interface. That is essentially a curvature-driven domain growth. But you can see here that we have quite large entropy of the domain wall energy, and also some internal structures in domain walls. And with the same machine learning model, we also apply it to this host time Hubble model. So essentially, we add this Hubble interaction to the host time electron lattice coupling. And because of the Hubble interaction, so you cannot just use exact diagonalization to solve the model and to generate training data sets. So we use the Gutzwiller stable boson methods. So this is a relatively cheap method for solving the Hubble model. And so we solve the system on like 20 by 20 lattice size and use the data set to train a machine learning model. And this is the large scale simulation results for U equal to 0.6 and 0.9. These are all well below the mode transitions. And by applying this to a few different Hubble U, then this is the time dependence of the characteristic length. And you can see that at very small U and at low temperature, we actually have this freezing phenomenon. That means that the domains, they start growing at long times. And then we have this smaller growth exponent less than 1/2 of this Allen-Kane behavior. But interestingly, when we increase Hubble U, we sort of restore the Allen-Kane behavior. So this is also quite unexpected. And I think this is perhaps the first study of how electron-electron correlation through this Hubble U affect the domain coarsening in an electronic system. Right. How much time do I have? 10 minutes? Okay. So maybe then I will just give another example application. So, okay, more interesting one. So we also apply this to the this Falico-Kimball model, another model proposed to study strongly correlated phenomenon. And in this case, we try to, so basically in this case, you have itinerary electrons and coupled to these so-called F electrons. But the F electrons, you can model them as classical lattice gates. And so we are interested in this Monte Carlo random walk simulation of these F electrons. But like in order to do Monte Carlo simulation, you need to compute the energy difference when you move this F electron to one of the neighbors. And each energy calculation requires diagonalize this Hamiltonian. And so to do one F electron update, you need to consider the energy difference of moving it here, 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 and here. So you need to do 4 exact diagonalization for one F electron update. This is super time consuming, especially for large systems. And even KPM is not of much help in this case. So the idea is just to build a neural network to predict this delta E. And once you have this delta E, then you know how to compute the metropolis probability. Then you can do large scale Monte Carlo simulations. So this is the benchmark, and then we do apply the trained neural network to simulate very large system. And the system is supposed to exhibit this phase separation into checkerboard states. But we find that the size of the checkerboard are very small. So some sort of freezing is happening here. But if I label the particles as green and the blue, depending on whether this F electron is on A sublattice or B sublattice, then you can see that there's some sort of coarsening going on with the sublattices. So even though the checkerboard cluster remain very small, but they sort of try to stick with each other and form this, we call these superclusters. And if you introduce some parameter to characterize this supercluster, there's some sort of hidden coarsening going on in this system. And again, this is only possible if you do machine learning and then do large-scale simulations. Okay, another application of the machine learning first field model is to simulate the itinerant electron spin systems. So generally, this kind of system can be described by some electron Hamiltonian, and there is this local on-site exchange coupling between local classical spins and itinerant electrons. And we are interested in the dynamics of these classical spins, but in order to compute this effective field, you need to compute the energy of the system, and this again requires diagonalization or other many-body methods of solving this Hamiltonian. Right. And these systems are important because they are host of many complex spin textures and also important for spintronics. So we applied this approach, and then on triangular lattice, we successfully reproduce the representative non-trivial orders like 120-degree order at half filling and tetrahedral non-coplanar order at 1/4 and 3/4 filling. And with the introduction of second neighbor hopping, we can also reproduce Skyrmian crystals with the machine learning model. And this is an application to study the phase separation phenomenon in a double exchange system. And this is apply this model to study this chiral domain coarsening in this tetrahedron order. So this particular order is a 4 sublattice spin order. And in 2 dimensions, there is no true long-range order, but this chirality of the 4 spins is a Z2 symmetry, which can be broken at finite temperatures. So we are interested in the coarsening of these chiral domains. So this here, blue and red are the spin structures with opposite chirality. And then you can see the coarsening follow this almost linear behavior, which is also totally distinct from the Allen-Kane behavior. And this, again, can be related to the spatial morphology of these chiral domains. You see a lot of this very straight interface. So this curvature-driven mechanism cannot be applied here. Right. And we also implement the CNN type of model to do the spin dynamics and also descriptors for spin glaze. Okay, so this is the part I would like to spend a bit more time discussing. So like I mentioned, one of the paradigm of this machine learning force field model was this beta polynomial machine learning structure. So you take the neighborhoods, you send to either equivariant or descriptor, then you predict this local energy. And then from the local energy, you sum all the local energy, you get total energy, and you do automatic differentiation to get the force. But the problem is that with this approach, your force has to be conservative. And for electronic system like driven by some voltage or other external source, it is out of equilibrium, and energy is not even well defined for such systems, so the resultant force is also non-conservative. That means that this famous beta polynomial architecture cannot be used to represent non-conservative force and for non-equilibrium electron systems. So, to generalize this beta polynomial structure, so we noticed that in non-lattice dynamics, the spin length is fixed. So you can think of this like particles are confined to the surface of a sphere. So then we apply the Helmholtz-Hodge decomposition on the sphere. You get like this gradient term and this curl term on the sphere. And if you rewrite this in terms of the spin directive, that means that the most general local field has 2 components. One is this famous non-lattice term, and this is a new term which can be responsible for the non-conservative part, right? So then we get this generalized non-lattice model described by 2 potentials. One is this quasi-conserved energy, and the other is this potential energy, we call this G. And this part can represent energy gain or energy loss. For example, if you set this G to just minus lambda E, then this is the non-lattice damping. And if you set this to like this exchange interaction form, where MP is the magnetization of a reference or pinned layer in a magnetic tunnel junction, then this term can represent the spin transfer torque. So these are 2 potential generation of the non-lattice equation can account for both energy conservation and energy gain and loss. So we apply this to a voltage-driven double exchange model. So you have this electron and coupled to local spins, and we're interested in the spin dynamics of this driven system. But since it is driven by a pair of external voltages, so to solve this model, you cannot just use exact diagonalization. So we use non-equilibrium Green function methods to solve the electronic problems. And so the local field, which drives the spin dynamics, is given by the laser Green's function. And then you need to do this matrix inversion to get the retarded Green function and then get the laser Green function. So this is a very, very time-consuming computation. Mainly because matrix inversion is already takes a lot of time, and then you need to do this for many different energies in this energy integral. So for example, if you include like 2,000 energies here, then you need to do 2,000 matrix inversion at every time step of your simulation. Very, very time consuming. So we managed to do this. We run this with multiple parallelization for like 2 weeks to get this voltage-induced metal insulator transition. And then we use this data set from like 30 by 20 lattice size to train a neural network based on our this two potential architecture. So this is a generalization of the barrel polynano architecture. So again, you take your neighborhood spin configuration, you do your descriptor, fit to fully connect neural network. But this time we predict two local energies, epsilon and the gamma, and you sum all of them to get this total energy E and the G, and from which you get the driving force. Now this part, the G part, can represent energy gain from the external voltages. So this is the prediction, and this is the benchmark with the non-equilibrium Green's function non-logistic simulation and with forces predicting by machine learning. And you can see the agreement is very good. And one advantage from this approach is that we can also, this is also kind of like the latent variable. You don't get this from exact diagonalization or from non-equilibrium Green's function calculation. So what is the ratio between the G part and the E part, which are the non-equilibrium and the equilibrium, quasi-equilibrium force? And we made the histogram of the ratio using the data from the interface. And you can see that the force is dominated by the non-equilibrium part. Okay, so this is a summary and some outlook. So I present a machine learning force field model for adiabatic dynamics or condensed matter lattice models. We apply this to electron lattice systems and electron spin coupled systems. And we also discuss various kind of neural network architecture. One important feature direction, we will focus more on machine learning model for non-equilibrium systems. And another feature direction is the adiabatic dynamics of emergent collective behaviors like order parameters or like in metal insulator transitions and their machine learning models. Thank you.
Any questions?
Yeah, sure.
So, very interesting talk. I think I missed sort of a basic point. So when do we know a force field model is good? Is the assumption that because of the inner side of this is always good if you are willing to take a big enough chunk as the
You mean how to benchmark the machine learning force field model?
So like as a guideline, how do we, because you're mapping, you're doing more than what I thought as force field chemistry. You're taking a quantum mechanical model
Yes.
and then making it into a spectrum model.
Right, but that's also exactly what people in quantum chemistry did. So the machine learning force field model is essentially a classical interatomic potential model.
I guess in chemistry, there's the entity, there's the concept of an atom or a molecule.
Right,
And here, if I have a Holstein model or a Hubbard model or something,
right.
and am I understanding?
Oh, yes, so the objects we are interested in this slow varying degree of freedom. So like lattice displacement or lattice distortion or like local magnetic moments. Right. These are like the classical variable in quantum MD is like atomic positions. Right, right. So that's basically the difference.
But the Holstein model is a basic displacement. And
Yes, I mean, the problem is like given Holstein model, even you assume these lattice variables are classical degree of freedom, it's very difficult to do non-equilibrium simulations, right? And so our goal is just to try to study the dynamical simulation of these typical well-studied lattice systems, right?
So in your slides of this generalized model, and introduce this G term for the loss, but why you still have a Gilbert damping term?
Oh, yes, so that Gilbert damping term is like the generic damping, but this G term is just, you introduce it, if you already have damping which can be captured by Gilbert damping, or if the original non-Dirichlet damping, then the G term would be mainly introduced to represent some sort of energy gain, like spin transfer torques. Right.
Any other burning questions? So if there are no any other questions, let's thank Gia-Wei again.
Thank you.
Since we have a planned schedule, let's come back at 3:30.